So our next talk in our leveraging Accumulo kind of track is about building scalable aggregation systems leveraging Accumulo. And we had to change it. This was the change of speakers that was in the program guide. So our speakers for this are Gedalia O'Brien, Senior Solutions Architect with CoVerse, and Bill Slackham, Software Engineer with CoVerse. So with that, I turn it over to Bill and Gedalia.
Thanks. So yeah, for those of you who came here to see Jared, he had a baby yesterday, so you're stuck with me and Bill. Jared, who was going to give this talk originally, is the one who submitted it. He and I and Bill kind of worked together to design the aggregation that CoVerse uses, the aggregation framework that CoVerse uses. So we kind of wanted to share with you today how we got to that design and then some technical details about it. So, this is just supposed to represent a view of what data looks like in your system when it's not aggregated, which is not very useful when it comes to human consumption. So, the first thing that people often try to do when they are looking at big data comes down to making some kind of aggregation so that they can start to understand what is actually in this data that I'm looking at, instead of trying to plow through terabytes of raw text or bits. So the reason that we created this framework for us was that we realized one of the most common use cases, like I said, for customers is going to be wanting to perform aggregations on your data. And having to build a custom analytic just to do a simple aggregation starts to become just a waste of time when you can have a more generic framework that can support some of these really common types of use cases. Can you all hear me okay, or do I need to lower the mic? Okay. So just some examples of aggregations that you might want to do are given here. So time series is a really common one. I've already seen a couple of those today because it shows a really nice view of kind of how your data is changing over time. Things like set size, I've seen that used again today. So unique users on your system, for example, that's a cardinality measure. Things like top K, so maybe the top K IP addresses that you see active at any particular time. Quantiles. Heat maps are another big one if you're looking at kind of geographical data. So we kind of realized that once we started thinking about things as aggregations, that you start sort of becoming obsessed with viewing the world that way. And you start to see everything as an aggregation. So this really has been very useful for us. So kind of just some background in terms of how we arrived at where we are currently. So the most kind of elementary aggregation you learn when you're in kindergarten is addition of integers. And the nice thing about addition is that you can parallelize it, which is perfect for a big data situation when you've got multiple machines working together. So we're so comfortable with addition that we might not think about why we can parallelize it. But it comes down to it being an associative and commutative operation. And this is kind of the basis for how a lot of these aggregation frameworks are starting to be built, is that you really need an associative and commutative operation as the foundation to your aggregation for a couple reasons. The first is associativity allows you to parallelize your operations because you can group together the integers or whatever operation you're doing. So the associativity, like I said, allows you to actually parallelize the work because you can compute little subsets of the answer on different servers and then bring them together, and it doesn't matter which subsets of information you have combined. And the commutativity goes into that too, because when you're doing these operations on a system like Hadoop, you're not guaranteed what order the data is going to be in that you're operating over. So it's really important that you can operate on it in any order and then combine the results together. So associativity and commutativity are at the basis for why addition is parallelizable and can be used in an aggregation system on a big data platform like Hadoop and Accumulo. So obviously addition is not the only operation that's commutative and associative, otherwise this would be pretty boring. So other, things that we're used to, like set unions, those are associative, commutative. So the community has sort of started to look at this through the eyes of an abstract algebra construct, which is called a monoid, and it doesn't really matter what it's called, and it's not something to be thrown off by. Basically, it just means that you've got an associative operation, and in this case, we're actually dealing with commutative monoids. So we are, building these constructs that are closed under associativity and commutativity, and you can actually build them as a generic sort of abstraction in a programming language of your choice, so that you can start to leverage them in a more generic way. And I'll kind of show a couple of systems that leverage this way of thinking. So there are a couple of papers out there, and we've given some of those in the references, that are kind of starting to look at aggregation frameworks through this lens of monoids. So as I said, given that this is becoming a little bit more popular way of thinking about things out there, there are actually some existing implementations. So Twitter's Algebird is one of them, and they have this monoid kind of construct and allow you to easily build aggregates for some of the kind of commonly used functions. And then the nice thing that we have found really convenient is that with some of these libraries that are out there, you can actually build your own aggregations really easily, and it's kind of more of a configuration type of thing. So as long as you have an operation that's associative and commutative, you can build it into one of these monoids and kind of deal with it in a nice abstract manner throughout different elements of your system. So hopefully some of this will become a little more clear when I kind of show you some more details of how these systems are put together. So one more key thing to remember about why these aggregation frameworks work, besides associativity and commutativity, is you have to be able to serialize your aggregates because of the fact that you're kind of passing them across the network. So, one of those details you might not think about right up front, but it's definitely something that you have to take into consideration when you're designing an aggregation system, is how you're going to pass that information around. Okay, so the key to all of this is that once you start to view aggregates in this manner, you can actually use this code throughout different areas of your system and kind of bring them together, and you don't have to worry as much about the implementation details of where that piece of code is actually going and being implemented. So I'll show you kind of an overview of a couple systems that are out there, and then we'll go into details of the actual system that we use, and then towards the end we'll give a little demo as long as we have time. So some of the aggregation kind of choices that we have out there, we're sort of binning them into two different categories. There's probably more out there, and certainly there are people in this room that know more about this especially than I do. So speak up if you disagree or have questions. But one way we're like, okay, so one way of viewing aggregates is kind of these SQL on Hadoop type queries, where you launch a SQL query, you're going in and aggregating everything to come back and retrieve it to view the answer to the question that you've asked it. The solution here has kind of a very different use case than we were looking at. In particular, the query latency is quite long. You're looking at minutes in general for queries like this to return. And it doesn't support a lot of users, and I'm talking, maybe hundreds or thousands of users. So this might be totally acceptable for other systems, especially where maybe you have a small internal system where you've got data scientists kind of looking at data. This is completely acceptable in an environment like that. And the one nice thing about this type of solution is that you don't have to pre-compute anything. You can ask questions on the fly, and you have that flexibility. So this is certainly a choice. It was not an option that worked for us in our situation because we needed the latency to be more of an online, so millisecond type latency, and we wanted to be able to support a lot of users. So we're viewing this as sort of falling into the other category, which we're calling maybe more an online incremental aggregation system. So Twitter does something very similar with their Hummingbird framework. Google's Mesa is also something that would kind of fall into this category, and that's the aggregation system they use for their advertisement data, and then the aggregation framework that we built in CoVerse. So again, the key there is sort of that lower query latency in the millisecond time range and being able to support a lot more users, so hundreds, thousands of users. But again, what we lose here is that flexibility. So we are kind of having to decide ahead of time what our aggregates are, what views of the data we want, and once you have that, you can pre-compute things and the answers are very quick. But you do lose the flexibility of like a SQL interactive environment. So there's trade-offs, of course, always. So let's see. I think that's some of what I already said. So these sort of online aggregation systems that I'm talking about now, which I mentioned Hummingbird, Mesa, and then the one we built on CoVerse, they have a few common things. The first is that aggregations are computed sort of incrementally in different parts of the system and then brought together. The other is that, like I said, results are pretty much pre-computed. So you've decided ahead of time what you want, what views you want into your data. It's important to note, though, that doesn't mean you have to decide ahead of time and then it's set for the rest of eternity. It just means that if you decide you want a new aggregation, it's something that you're going to have to put into the system and give it a little bit of spin-up time. So usually when we introduce a new aggregation, for example, it'll take maybe 5 minutes for that to propagate throughout the system and that to become a queryable thing. And that's, backporting it on all historical data. So you wouldn't only be able to query the aggregations on the data from the date that you introduce the new aggregation, but you'll kind of backfill it and then continue to go forward. So there is pre-computation involved, but the flexibility is at least there that when you want to introduce new views, you can at least do that. And then the third, which is the most relevant to this conference, is that all of these solutions store their aggregations in a keyed database. So, of course, we use Accumulo for that in our implementation. So, let's see, do it on time. Real quick, I'll just kind of show you the Hummingbird construct. Basically, Twitter has the use case of wanting to be able to compute aggregates both in streaming in Storm and then in batch in Hadoop to kind of combine the low latency of a streaming computations and then the historical kind of catch up. So some people would call this an example of a Lambda architecture. I don't think the Storm people like to, the Twitter people like to view it in that lens, but to me that's sort of what this is. But basically they wanted to be able to have the same logical code in different places in their system and not have to manage two code bases. So that was their main use case for wanting to use this monoid abstraction. And you can see kind of the green triangles are the different places in their system where they're using the exact same code, but it's being, of course, implemented on top of different technologies. So Google's Mesa has the same kind of thing where the back-end system is different, and they have a different use case than Twitter does. But again, they have the same reduction aggregation code operating in several different places in their system. One is kind of to do these back-end bulk compaction reductions of data, moving it in from smaller batches into successively larger batches. And then their query server kind of combines everything together. So then the last picture I have up here is the CoVerse architecture, which again, we're trying to use the same code in several different places, and we've used that monoid abstraction so that we can just manage one code base. And so it's implemented in Hadoop. So we have kind of these back-end jobs that are running on top of Accumulo. Excuse me. That are kind of doing calculations on the timeframes of minutes to go through and calculate different aggregated views that are configured on the data. And then those same aggregations are being applied within Accumulo in compactions and at scan time. So we're making heavy use of that Accumulo Iterator framework to apply the aggregations on the data kind of iteratively as well. And then finally, we actually do also have the ability to do some of those aggregations in our web server, which, if you wanted to do something like aggregate hour buckets into some cumulative day time range or something, that's the kind of thing you could do server side. So anyway, this is kind of just an overview of how these systems are taking advantage of looking at aggregations in this generic way, so that you can deploy it in different locations in your system and bring that all together in a more seamless manner to get these aggregated views of your data. So I'll pass it over to Bill in a moment and let him kind of go into the Accumulo implementation details, since that's probably something you'll all be really interested in. And then we'll try to do a demo at the end, like I said. Before I do that, are there kind of questions on this way of viewing aggregations? Okay, so the question was about sub-aggregations, so aggregations that you wouldn't want to necessarily apply to all of your data. So I think that's something you would have to build into your framework in terms of basically what your input data is to each aggregation piece of your logical aggregation. But that since that doesn't affect whether the operation is commutative or associative and basically would just kind of influence your input data, I think that'd be a pretty easy thing to configure into your system. I don't think it's something we've thought about. Like I said, when we configure our aggregations, they'll operate time-wise over historical data and then anything going forward. But really, in a way, you could also think of that as just an additional dimension to your aggregation. So if you were looking over, you just wanted, the last day or something, you could make that just an additional dimension of your window, your data cube that you're looking at. Does that make sense? So that'd be another option. And we'll have more time for questions at the end too. All right, I'll pass it to Bill.
Make sure this works. So now we're going to learn how we bolt this onto a Ferrari, if you're aware of the talk across the hall. So first we're going to figure out how we get all this data into Accumulo. We usually have a MapReduce job that runs our combiner logic, or our reduce logic inside of a combiner and a reducer, as well as in a Accumulo combiner. So when we're generating things in MapReduce, we generate R files. I chose R files over batch writer because when we generate the data, we can generate the files and try to import them. And if they fail, we still have the file and we can import it at a later time. So there's less logic when applying a mutation fails, and there's no partial application of our output. So it really simplified our logic. So it's not impossible to use a batch writer if you really wanted to, but I think that in the failure case, you have a lot more work to do. As a consequence of doing this, though, we're adding more files to the database, and therefore we have to compact them more often. And what we've seen at roughly a 20-node scale and about 200 jobs a day, because these things are running continuously over a stream, is that we actually haven't had to do anything, which is really nice. And I kind of think, my hypothesis, and I haven't proven this, is that when we actually aggregate a lot of data, we're actually aggregating it into very small final results. And usually, like when I see, in terms of just looking at counters in our MapReduce job, that we get 1 to anywhere between 1 and 4 orders of magnitude reduction in the number of entries that we're passing along at each stage. And then remember also that in Accumulo, once we do compact it, we're usually compacting down to a single entry. So data is relatively small in this table. So we do an iterator. We set it as a major compaction, minor compaction, and scan time iterator. And it's just a combiner. It takes the same logic we did in our MapReduce combiner and MapReduce reducer, and we just stuff it inside of an iterator so that later on, as we run more MapReduce jobs, we can combine all their outputs into a single key or a single entry. This is the code that we use for it. It's pretty simple. Earlier, Gedalia mentioned that we have this aggregator concept, or we have the monoid, and we created a concept called an aggregator, which just attaches the serialization and deserialization methods onto this function. You see that's some Scala code if you're not used to it. I like it just because functions are they're first-class citizens in the language, so it kind of makes it a bit more compact. And you can see what I'm trying to do here, which is Accumulo presents me with a key and an iterable of values. A value is just a wrapper around a bunch of bytes. So I can deserialize it. I can sum them up using this reduce solve method, and then I can just return my key and the summed value. So, and you actually will notice here that I missed the reserialization part, but as that method is attached to the aggregator function, we just serialize the sum and return that as a key value. And the important note is earlier, if you ever kind of read the Twitter documentation on Algebird, they always speak about associativity. I think the guy even dropped an F-bomb in the video mentioning that, no, don't worry about commutativity, don't worry about it all. It becomes a concern for us because Accumulo will write new files, and occasionally depending on your compaction strategy, you'll have subsets of files be combined at once, and they're not necessarily in order. So we always want to arrive at a correct answer. We just don't care how we get there, and that's what being commutative helps us do. So this is the table structure that we kind of settled on, where the row is this kind of interlaced pair of field names and field values. The column family describes what kind of aggregation we're doing. So we have things like count, sum is count, like list append, time series, count min sketch, which is a way of kind of estimating top K and cardinality while also preserving the keys. We do have a visibility. The column qualifier is actually what I call a relation. So the best way to think of a relation is when I say that, let's say I have a database of my flights, or I'm aggregating them, right? And I want to say how many times have I had to fly to Colorado? What I'll do is I'll have my key that says, okay, well, this guy, the origin city is BWI, and I'll have this value in here I'm relating to my destination. And in that value, I can aggregate things that say oh, he's been to Colorado 10 times, he's been to San Francisco 1 time, he's been to Hawaii twice. So the relation is kind of this thing that just attaches field metadata and gives more context to the value that you're summing up. And we'll actually get to that, I think, on the next slide, which is kind of nice. And of course, I don't really use the timestamp for anything, but the value is, of course, the serialized value or the serialized results that we're aggregating together. The visibilities kind of they're a little weird because we can write any visibility we want. We can filter on visibilities pretty easily. At scan time, we can kind of combine them. But there's kind of this logical question of what do we really mean when we combine something that, say, is public and private. So let's say I have a collection of just Facebook photo albums, and I have an album, I have a public count and a private count, right? Because I have all the photos I shared with my friends, so they've seen all the breakfast I've been eating, but maybe they don't see I don't want my grandparents to see what I do with my friends at night. So I have a total of 900 values, or 900 photos, but the visibility there is public and private. So if I was going to aggregate these into a single entry, what would I label them? And that's an open question for us. Maybe the other answer is you just don't care and you drop it. Like if I was writing an app, if I was writing the user interface for Facebook for these photo albums, and I know you were querying it, I don't need to know it's private because you're the one viewing it. But that's certainly not a workaround for all cases. So when we query this bad boy, it's kind of geared towards point queries, so you have to kind of know the fields you care about, the dimensions, and the values. So if we go back to my flight example earlier, I need to know what, say, my origin. I want to know the origin and then the actual value. So we look at what's a good query. So what are the top K destinations from BWI? And that would end up being this, usually an estimation just for size purposes, but you can keep an exact count of things like Colorado, Hawaii, San Francisco, Miami. But you really wouldn't want to do something like, what are all the dimensions that I have for BWI? If only because the key schema doesn't really provide a good way, or doesn't provide enough context to tell you that that's all the data you want. Like when I roll over different aggregations, are they all related to the query? We just don't have enough context for that. And so this is what, I don't know if anybody remembers, one of like the first kind of public uses of Accumulo was this app called Trendulo. And luckily Jared, the guy who was going to give this talk, is the guy who made that. And so this is kind of, we did a little demo here, and you can see that we kind of track Twitter mentions and hashtags, and then we also have kind of a comparison of exact and approximate top K of just some emojis sitting out there. And they're actually pretty close, which is neat. And hopefully we can get you a live demo in a second. And quickly, everybody jot down all the references so that you can go back and either call us out on something or say, oh, this is cool, I can use this in my application. Do we want to go to the backups? Or?
Yeah, no, I
Okay.
don't think we need the backups right now. And yeah, it sounds like all the slides will be posted online too, so you can kind of look at the references at that time. So you can see kind of up here a time series. You can't see the query box, but it was for breakfast, lunch, and dinner. And you can just kind of see the diurnal effect of the fact that, you know, people mentioned breakfast around breakfast time and lunch around lunchtime and dinner around dinner time. So this is, you know, a little bit of a silly example of how you can use an aggregation framework, but it really does illustrate a couple things, which is that you can easily calculate different kinds of aggregates. So, you know, we have a time series here. We've got top K over here, which is just showing the different emojis that are present in the data. So yeah, the unique users are a cardinality estimate. So the cardinality estimate and then the approximate top K are kind of these probabilistic data objects. But you know, all of those things are examples of commutative and associative operations, and you can easily configure them all in the same framework. So basically, we just went in and configured an aggregation for each one of these things, for each one of these dimensions of the data, and then you can build a little app that's on top of that query framework that Bill was just talking about. So you know, you can look at things like this and see, you can, you know, kind of see when the rioting started happening yesterday. And then there was a little bit on Sunday too, I believe. You know, so these kind of views of the data are really fun and important because it allows you to pick out things from the data that are clearly interesting. And then once you see those things, you can teach your algorithms to go back and find when those interesting events occur. So you can look for, say, peaks in a time series, and then look for anomalous behavior or predictive behavior on top of that. So there's lots of neat insights and follow-on work that you can get from looking at some of these aggregations. And then kind of on a lighter note, you know, if you wanted to look at something, I think there was like a baseball fight last week. You can see when that happened. And then finally, you know, you can build things like we have different aggregations views already done so that, you know, you can look not just over the last 7 days, but over the last 24 hours and kind of get a more granular view of the data. So we are almost out of time, but we'd love to take questions if you have them. Yeah. Right, yeah, so that Accumulo table that Bill just showed and kind of that query, you know, so these are all point queries out of that table, so that's why it returns in that millisecond time frame.
When you use Solar for that, you actually get kind of like a much more generic view of things, like you're actually computing, it's built in to compute these things. I think that the foundations are very similar, but automatically we have not built something to run through and build like a graph to build like actual even facets or human defined facets. Like that would have to be user code. But I don't think there's anything stopping you. It's dependent upon the data structure you want to use and if it adheres to these rules. So if you, like, we can at least build things like, we can build an aggregation in a cube pretty easily, or we can look at, like I said, top K earlier. But actually getting that, or reorganizing your data is something that is kind of a manual labor. So this little box up here where we say the last 24 hours, or the last 7 days, or last 30 days, we actually define time boxes to generate that. And unfortunately, we didn't get to show it, but we have a little Scala DSL that lets you describe how you want to like filter a record or massage it into something like generate time boxes based on a time field. So you can definitely have this kind of like fan out of different views of your data when you're building these cubes. It's just a manual effort at this point. So that's at some point, like if you want to dig deep in this, Algebird, which is the Twitter library that we're using, it mixes in certain traits into the functions that it's defining, and commutative and associativity are part of that. So when you get a monoid, usually you want to check the traits to make sure. I don't know if we actually truly enforce that. Like in theory, you could write a function that wasn't commutative or associative, and you kind of get some garbage in there. But I think there is a way. It's still, like I said, somewhat manual, but we have the traits. We can build it. Well, so these are. I mean, they're running in real time. Like, if you have a data stream, right, where we're constantly analyzing that stream, it's technically pre-computing, but we are sending it all to the same place to be reduced with previous data. Correct. Yeah. Once we write it to Accumulo, that new data, as when a reader comes in or a compaction comes in, it's viewing that new data as long as it's been loaded into Accumulo.
Yeah, and so that's the advantage, right, of having this same logic applied in different places in your system, is that as new data is coming in, you can compute those aggregates in the Accumulo compactions. You don't have to wait for, say, a MapReduce job. Good question.
Yeah, and I know we did have like heavy mention of MapReduce, but in theory, this should apply to at least transactional Storm, which I think is called Trident, and Spark. So the compute framework isn't the essential part here. I think the Accumulo part, where we can send all the data to the same place and combine it there as well. So the new data and the previous data is kind of like the key part.
All right.
All right.
Thank you, guys.
Thank you.